Hi there. So my name is Inouk, and I'm the co-founder and CTO of a company called Foobot out of Luxembourg. So in 2013, we thought we needed a kind of thermometer for air quality, and not just for CO2, but also for harmful stuff like chemicals and fine dust. So that is our first product that you see here. It's called Foobot. And since we were on the market first with this type of product, we attracted a lot of interest from the academic world. We have actually about 6 research papers published either using or analyzing the accuracy of our device, and most notably one from the Lawrence Berkeley lab out of California. Monitoring is great, but to improve air quality in customers' home is not that easy, especially when you rely on the homeowners to take action. So one of the things we did was to propose an integration of our sensor with the Nest thermostat. So just to be clear, in the US, the thermostat is controlling the home ventilation system. It basically blows hot or cold air. Most houses have this kind of forced HVAC air system and no water-based heater like we do have in Europe. So with an algorithm, we started to send comments to the thermostat so they can blow more air when the air quality is bad indoor. And as you can see, it works. On average, we reduce the fine dust and the chemical pollutant in these homes. One thing that may come to your surprise is that with our algorithm, we actually didn't need to ventilate more. We were able to reduce the ventilation by about 10%, and that's some savings on the energy bill for the homeowners. So this experiment in residential building laid the path for our new service that we are introducing now. We call it Smart Air Building. And the goal is to optimize HVAC system to reduce carbon footprint and improve air quality. So now let me lay out how this works. So basically at the center of our system, you have an AI agent. And this agent is deciding every 15 minutes what the best HVAC settings for the building is. It gathers external data such as weather forecast and outdoor air pollution. And it can also get data from our B2B sensors that you can see on the bottom right, though we can also use external sensors from the building. And then based on all of this data, it takes action. It takes a decision and it forwards this action to the BMS system of the building. So now let me explain a bit one of the critical aspects of any artificial intelligence application. It's the training workflow. And in our case, we use kind of a digital replica of the building that is called a building model. So so we are able to let the agent train in a simulated environment, and then the AI agent is ready to be deployed. So one of the unique aspects of this technology is that we don't spend weeks collecting data in the building. The agent is ready from day one. So to detail this a bit more, to create a building model, we use OpenStudio. That's a tool from the US Department of Energy. Our model doesn't need to be extremely detailed, actually. It has to correctly reflect the building envelope and the HVAC system. Then we calibrate the model against real-life data from the past, so it aligns with the existing energy bills and weather history in the building location. For that, we follow ASHRAE 14 standard, also out of the US. And in the end, we have a digital twin that reacts as the building would in real life. The digital twin is then acting as a playground for the agent to train. We use deep reinforcement learning for that through OpenAI Gym. We combine with Energy Plus simulation, which is also from the DOE. We are able to simulate millions of scenarios that are equivalent to decades of experience for the AI agent. And then we are able to benchmark different control strategy. That's what you are seeing there. So you know, the agent is not replacing a full feature BMS. We actually only choose a small number of parameters on which the agent will act, and the rest is left for the BMS to work. One of the advantage of this approach is, I mean, of this whole digital approach, is that you can basically predict results before deploying anything in the building. So now let me explain you a bit what we did in our first building deployed. So it's a rather large building in Denmark, built in 2015. And it's quite modern in terms of comfort and energy preservation. We started our system back in October, and since then we saved 52% on HVAC system energy, and we were able to maintain 99% thermal comfort. Also, 100% of the time the indoor air quality is maintained below acceptable threshold. So in that case, the simulation, so the step that was before, it predicted 44% savings, but we haven't covered the full year cycle yet. So we may see what's with a 12-month cycle, what's the global energy would look like. Though you can see that from the first day when the agent started to take control, it drastically reduced energy usage. So in this building, the air quality is measured by our proprietary sensors, FoobotSAT, and the facility managers, they have access to a web dashboard to monitor it in real time. So as a summary of the performance, we project to save 62 tons of CO2 emission and 51,000 euro worth of energy over 12 months in this building. This is the first one, and we are currently deploying the technology in several others in Europe and the US. So thanks for your time today. But before we go, let me tell you that we are interested in any type of collaboration with the academic world. I mean, that's what we did back with our first product, the air quality sensor. And we are really looking forward to do the same with this service. Also, if you want to know more about the technology and how come we can save so much on the HVAC systems, check the link that is displayed here. There is a really detailed strategy there. And as usual, we are quite transparent about the technology we use. So feel free to contact us also for any type of project. So thanks a lot for organizing this webinar. I was really glad to be part of it. And I guess now I leave the floor to the organizers.